Hello everyone, it's May the 14th. We're back at the old setup and back at the old time because today is a very, very long day. I was doing an almost impossible task. I want to submit a paper to a conference, but the requirement is, hold on, I need to let my cat out. Ah, strange. My cat meows, but he's not there. I probably have to do another run later. Anyway, so what I was saying is I want to submit a paper to a conference, but the conference has a limit, right, on the page numbers. The paper initially I wrote was no with no page limit in mind. I think it was like 14, 15 pages, and and the conference paper requirement is 6 pages. So I have to shrink 14 pages to 6 pages, including the reference. Is not an easy task. All right, so I'm gonna take a little mental break by doing LeetCode, and hopefully that when I get back to doing the old to shrinking, I have a fresher mind. I'm able to shrink it. I'm already at like 7.5 pages, so I think there is a light at the end of the tunnel for this. Anyway, I think the cat is meowing again. Let me do this again. All right, this time the cat is out, so we're good to go. Flatten binary. Oh, I think I've done this before. Maybe. Okay, so given a root of a binary tree, flatten it into a linked list. The linked list should use the same tree node class where the right child pointer points to the next. Okay, and that is always no. Should be in the same order as pre-order traversal. Oh, what's pre-order? 1, 2, 3. There's a root and a left, right? Root, left, right. Root, left, and then 4, 5, 6. Okay, root, left, and right. That's fine. Okay, number of nodes is 2000. Values. Can you flatten the tree in 01 extra space? The cat is meowing. I don't know what he wants. He's a very weird cat. He wants every door to be open, but we don't do that in the household. Some doors are closed. Okay, so oh, of course. Like if you don't do 01 space, it's very straightforward, right? If you don't do 01 space, you simply create a separate list, and then we're done. You traverse, and then a separate list, and we're good to go. But the requirement here is we need to use 01 extra space, which means we have to do some manipulations on the trees. Man, today I just don't have a break. I just find out that my laptop got some sauce on it. I was eating earlier. Damn. Come on, I want to catch a break. All right. Okay, so we have to modify based on this, right? Oh, modify based on the tree itself. It's interesting. So root. Maybe we cannot do. Ooh. 01 extra space. No, I haven't done this before. So we have to use the right right? So the right is connected to something, which means if it's connected to something, recursion first. Let's think about, can we do recursion? So recursion will be, this is the current node, right? So what we want is to have its right node connect to the next, right? So I want this right node connect to the next. So we know the next will be here. We'll go this. So we can take its right node out temporarily, and then we say we go to the left, because I know that the next one will have to be taken from the left node. And then I'll go to the left, compute whatever the traversal is on this, and I will attach to that. Then what? Then we need to know, so this has to return, I have to return like two nodes, the root and the end, right? Because I need the end so that I can attach this one, attach the right node, and we also need to do the right node side and attach the right node to this, and this one will return its root and end, and this one will return the root and the total end. Okay? But is recursion really all one extra space? Let's try it first. Actually, I'm not sure how this works. I mean, it does work, but what is the end state? The end state will be, we go this, right? This is the end state. We're gonna go left. Left is a null, which means I have nothing. But on the right side, I have also nothing. So this one will return what? No, on the right side, I need to return myself. Yeah, I am. So if I'm in a leaf node, then I return myself. So for this one, I say I take this one out temporarily, and I say this will give me the root and the leaf, which are both itself, right? So attach, and then this one attach this, root and leaf will be itself, and then this one will return. Okay, let's try it. Let's try it. Maybe it works. Maybe. Every time I say maybe, because I am not confident in all these endeavors. I mean, this is, I was actually thinking, I was talking about this today earlier. Like how long do I want to keep doing this? And the conclusion is I want to do this forever. I mean, not sure if I can really do this forever, but as long as there is a platform for me to do it, I do want to continue to do this, right? Even if, say, like in the future, I find a job, I graduate from what I'm doing right now, I find a job or not, right? I still want to do this because it's fun. I think it helps me keep myself sharp. So just have a node, which is going to be a tree node. Oh, I also find some Python libraries today, which is quite interesting. If I have time, I'll share with you in the future. Not in the future, after I finish this problem. So what do you want to return? I want to return two things. I want to return a tuple, right? A tuple of tree node. Tree node and tree node. And we have to add tuple here. Okay, let's just use, we're on Vim. Okay, so what do we do? If, we say if, hold on. Is it, what if like a 5? How do we do this? Its left is nothing, but its right is something, right? So what do? We take it out, and the right Oh, and it returns itself. Wait, what? This one will link to, it's supposed to link to this, and we have the tail. So it's all itself. Hold on. Which means if the left is a null, right? If the thing's left is a null, then, okay, so we say if node.left, right? Then we say next head and next tail equals self, no, equals helper, node.left, right? Else, then what? Next, head is itself, right? The head is always itself. For each node we go in, the head is always itself, and then it's always about the tail, right? So the tail, so if I have a left node, then I get the next. If I do not have a left node, then my next head is myself, and my next tail is also myself, right? And then we say this dot right equals next head, and I cannot point to myself. And the tail, hold on, next head is going to be, otherwise next head. So what we want is my right is pointing to the next head, but the next head is myself, so I don't do anything. And then we also need the next tail. The next tail is also myself, which is fine, right? So when I say else next head is going to be next head, next tail, going to be none, and the node myself, right? If node are left. And after that, let's say temp equals node are right, right? And now we say node if next head, then we say node.right equals next head, right? And then what? And then we're gonna do helper node.right. All right. So this is node.left, and again, so it's the same. So if node.right, then node.right next head. Next head, next tail, next left head, next left tail. Yeah, I think it has to be next head left and next tail left. And then this is going to be left. And then this is also going to be left. If next head left, then node.right equals next left. Okay, and then this is going to be right. And next tail right equals helper node.right. Else, right? Else we're going to say next head right and next tail right going to be equal to node.right. next head. Hold on. If node.write, if node has no write, then on the right side, if this one does not have, so on the right side, and I do the left side already, on the right side, it should be nothing. It should be none. Both should be none. None and none, right? Both should be none because the right side is nothing. And then what we do is, also let's do the, that's fine. So we do, yeah, let's do the left and right first, and then temp.node.write, and we say if next head left, we have the left side, then we say node.write equals next head, and then we say node actually don't need this because we do this already. And then we say node, so node.write equals next head left. And then we say next head, next tail left dot right equals next head right, right? Next head right. If we don't have it, then it's going to be, what if I don't have it? What if we don't have 4? 2 is going to get 3, and then I'm going to get 3, and we're going to return itself, and then if node doesn't have a write, right? If node doesn't have a write, then what do we do? If node doesn't have write, then we say next head right is going to be none, because that is going to be hold on. Next head right is going to, but what we're going to return, right? What we're going to return is node, myself, and the end. So the end is going to be like, if we don't consider 4, right? So this one return, we should return 2 and 3. 2 we can return. How do we return 3? Now 3 is on the left side, which means we're going to get 3 as the next tail left, right? And if I don't have a right side, then I do not attach anything. If I do, it has to be a node, right? It has to be a node. If I do, because this has to be a node. I would say left is nothing, and then we don't do node.write. We don't attach anything. And then we also say next tail left is node. So this basically say node.write equals next head right. If next head right exists, if next head right exists, and we do this, right? And now we want to return. So we say we're going to return node, that's the start, and next tail right. If next tail right, else if next tail right doesn't exist, then we say next tail left. So that's helper. So let's say if we have a 3 coming in, right? With a node on left, node nothing, so we're gonna say none and node itself. And then node on right is nothing, so basically that'll be none. So next hit net, nope, we don't do this. Next hit right, nope, we don't do this. So we return node, 3 itself. And next tail right is none, so we're going to return next tail left, which is node itself. So we're going to return 3 back to it. So on the 2, next left is good. So we're basically going to return 3 and 3, right? Have 3 and 3. And node on right is 4, which is same as the 3. So this one will return 4 and 4. So for here, we say if next head left, yes. So node dot right, 2 dot right equals 3. Okay. Now next head right is going to be 4. So we say next tail left. Next tail left is also 3. So this right to 3, and it's also 3. 3 dot right equals next head right, which is 4. And we're going to return node is 2, and next tail right is 4. So we're going to return 2 and 4 back in here. This might be correct. So what we do is we can call helper root. We don't need to return anything because we're going to return. Yeah, we just let's say do not return anything. Okay, we're not returning anything anyway, and because it's tree, so we usually do not do any test cases because we don't want to write a test case. Okay, let's take a look and see if this one's correct. Oh my goodness. This does not look right at all. Alright, I think we... shoot. 1, 2, 2, 3, 3, 3, 3. What the hell is this? Your answer. I think I can show basically what is this? Oh, 1, 2, 3, 4, 5, 6. We did it, but we screwed it up. Screwed it big time. Okay, so what happened? Well, what happened is we never cut the left. That's what happened. Okay. So like when we get left and right, we need to say node dot left equals none. And cut the left, and then return. This is not right. Let's do this again. It looks promising. Yeah. Okay. Test edge case. Number of nodes could be range 0 to 2000. So edge case number 1, empty tree. Always test empty tree. That should be empty. None type has no attribute. Okay. That's true. So we should say let's say if root, right? If root, then helper root. So that handle the empty case. Now single. All right, 1, 2, 3, 4, 5. A single node. Okay. And let's also add a good case, right? So the simple, a full tree, a complete binary tree. Is that considered complete? I forgot the terminology. Looks good. What if we do a very, okay, I think it's no. 3, no. for very unbalanced, no, 5, right? Unbalanced, see if this one works. This one works. How about a 1 that's unbalanced on the other side? 1, no, 2, no, 3, no, 4, no, 5, right? So it's already correct. Okay, I think this is correct. Pending, accepted. Okay, so this is correct. We just need to, yeah, there's a slight change. So I'm going to copy and paste onto this. Yep. So, and this is a considered, I mean, this is a recursion solution. So technically speaking, it is not a 1. But we did make all the changes in place. All the changes in place. The idea is that given any root node, we want to process the left child and return the head and tail of the linked list, right? Of the linked list converted from the left child. Then we do the same. We do the same on the right child, the right subtree, not child. Call it subtree. The left subtree. From the left subtree. Then we can construct the linked list based on the current tree by doing root .right equals left head, and then left tail .right equals right head, and finally we return root and right tail. The tricky part is handling nodes with no left or right child. No left or right child. Another tricky part is to not forget setting node left to none. After these two tricky parts are resolved, the problem is solved. All right, let's take a look. The runtime is ON. Yeah, runtime is ON. So it's the ON runtime with 74% ranking. With what? 36 seconds, milliseconds, 36 milliseconds. The memory, I think this is considered 01, right? The memory is considered 01. Okay, let's take a look. No solution for this. This is a medium question, like problem about it. And I think it's a good question as well, because there are two levels you can do, right? First you say, okay, that we don't have any requirements on memory usage, like try to design. That'll be very simple, but like kind of a basic idea of how strong the candidate is. And on the second, the follow-up, you say, okay, how about we do not allow you to use extra space, but we do allow you to use recursion. That's the second. And I'm 100% sure people are going to complain that recursion is not O1 in space. All right, we're going to check the non-recursive, that's for sure, but oh my lord, that's it? I am impressed. I thought mine was good. Huh. Wow, holy moly. All right. Post-order traversal. Wait, is this? Hold on, people are explaining it. People are explaining it. Hold on. Flatten root dot right. Then flatten root dot left. Pre. We have a private value of pre. Root dot right equals pre. Root dot left equals no. Pre dot root. What? wait, what? Flatten root dot. Okay, so we have a root for left and right. On a flatten root dot right, okay, and then flatten root dot left. Then what? Then we say root dot right equals pre, and root dot left equals no. That's understandable. And pre equals root. So we have a pre that keeps changing. That must be the trick. I can't see this because root dot right equals pre. All right, so if we keep going, right? So flatten root dot right, so root dot right all the way down to the most right. So the most right root is gonna be no, so our term. So to the right leaf, and we've done root dot right, which didn't do anything. Now root dot left, if it's a leaf, that's also didn't do anything. And then root dot right equals pre, which is no, okay. Root dot left is no, okay. So pre equals root. So pre becomes the right leaf. Then we go a step further. So flatten root dot right, what it does is pre becomes the right, becomes the leaf, because the leaf is done. Now the previous one, the cause, all right, so we say it's like that, right? So now we call root dot left. Okay, so we call root dot left. Let's say the root, the left and right is just a complete minus 3 with 3 nodes, right? So we call root dot left. And after I call root dot left, the left will call right left, and nothing happens. Then root dot right equals pre, which is currently the last node. Okay, that's correct. Root dot right and root dot left is, and then pre equals root. Holy moly, this is correct. Now we already constructed the linked list on the end, at the end. Okay, and then go back to the root. Root dot right equals pre, because pre is now, oh my god. Oh my god, how did you come up with this? How did you come up with this? So this is a, what do you call it, a post-order traversal, a right-left root order. Yeah. So I think because it asks you to do a pre-order which is root, left, and right. And after you do root, left, and right, they want you to put it on the right side, on root, left, right. So with this order, it is equivalent to doing a right, left, root. And right, left, root follows a good trajectory because right will be the tail. So if you do root, left, right, then root is the head, right is the tail. You go root, left, right. And if you do right, left, root, then it can be done with this simple solution. Yeah, they do root out right. Then we go right first, and we do the left first, and we make sure that each time we update the pre, right? We update the pre, which means the pre always points to the head of the linked list that my current node need to connect to. That's what the pre points to. So we always go root or right to connect to the pre, and after doing that, the pre becomes root. Oh wow, this is marvelous. Holy moly, how did you come up with this? In reverse way, we get we go left or right, left. So we'll go right, 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 and then left, or right. So 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2, 1. Reverse order after flattening is post order traversal. Yeah, traversal need to tree in this order, and then set each node's right pointer as the previous one. As such, the right pointer behaves similar to a link in the flattened tree. So we traverse this way, and then we get this out, right? So every time we get this, that's the root, and we say root dot right equals pre, which says a none, and then we set the pre to this. And then this dot right equals pre, this dot right equals pre, and then we basically reverse it. Oh wow, holy mother of Lord, this is good. This is very, very good. Versed pre-order. Yeah, that's just technicality. Wow. How you come up with this? Printing nodes in reverse pre-order. I mean, we just want the order, right? What we want is an order, and we can do the order in any fashion, like the pre-order and the post-order. So the post-order is the reverse of the pre-order. Now we can do pre-order, but the problem with pre-order is every time we get the node out, right, we visit the root first, and then we visit. This is the pre-order. We visit node first, and we visit the left, and visit the right. But the problem with pre-order is after we visit the left and after we visit right, we need to return something. That's what I did. I need to return something in order to construct a tree. But here it's post order. which means when I get back to the node, to the root, the tree is already done. But why can this not be done though? The post order will guarantee that after we traverse, so we traverse the right left first, and the right left after I traverse it already become a linked list, and with the head, with the correct head. But we do pre-order, traverse left and right. If I traverse left, and then I traverse right, how do we make sure that a right will be pointing to the right place? That's the thing. You cannot be sure that the right will be pointing to the right thing, right? That's why I have all these variables, because I need to make sure that after I traverse the left and I traverse the right, the resulting linked list will always find the right place to link. And it cannot, because the left could be different sides, so you don't know where the end is. But the beauty of this is after you traverse right and you create whatever, you know the root, the head is certain, the head is always right, right? And then you do the left, and when you do the left, but don't you still have the same problem? You do the right first, and then you do the left. And after you do left, how is the left is automatically connected to the right? Which part? Well, because it's each individual node, right? Each individual node is doing this. Oh, because we're always looking for the right, right? So we go for the right, and let's say like on the right tree first, or right subtree first. So on the right subtree, let's say we do the flatten. It's a flatten. It's good, right? And we have its head. Now on the left subtree, because we are doing post order, so we always find the rightmost node. So once we find it, we can immediately attach it to the head of the right of the flattened right subtree, right? We really can do this. So that is the beauty, because every time we look the rightmost, right? Every single time, it's always the rightmost. So we can always just keep adding on top. But here, every time we're looking at, well, we don't look at anything, because we do node first, do the root first, then we go left. That's the problem. I think if we do left first, so every single time we always go left, it's not going to be correct, because it has to be node. Yeah, I think it has to be the post order, the pre-order. That's why the pre-order and post order, they're the mirror image. Yeah. Yeah. Wow, this is very good. This is very, very good. Non-recursive. Oh, it's the same idea, right? You see? We traverse the right first. Traverse the right. And we have a now. So pre-right equals now right. Left subtree replaces right subtree. Oh, it's just iterative on the recursion is always hard to understand. So if now has a left tree, then we're gonna go right first. After the right, then now equals if it has a left tree, then we go pre equals now to the left, and while pre, wait, what? That's not the same. Oh, now to the left, then we go to the left, and then we say pre equals now to the left is this one, and while pre to the right, we go all the way to the right. Pre, and then when we get out, is pre to the right is nothing, right? So that's the rightmost node of the left tree, left subtree. And we say that is going to be the, isn't that going to be the tail node, I think. Yeah, that's the tail node. So pre to our right equals now. Where is now? Now is here. Now right. That is correct. That is correct. And then now the right. So pre the right goes now the right. And now the right equals now dot left. Huh? This I don't understand. Now the right is on the right subtree, and so now the right equals now the left. Now the right, hold on, so we say pre the right equals now the right. Okay, that one I understand. And we say now the right. Oh, now the right. Hold on. Pre dot right equals now the right. And then now the right equals the head is now the left. Yes. And now equals now the left. And now the left is nothing. That's cool. Then we say now equals now the right, which is the next node. Then we go back, do the exact same thing. Oh, good. Is the current node's left subtree to replace its right. Current node's left subtree. Replace its right subtree. The original right subtree is already linked to the current node's pre-node. Time is over. Yeah, it is over. Morris. Yeah, it's a Morris traversal. I mean, it's basically it's finding the rightmost node on the left subtree for each root. Finding the rightmost node of the left subtree. That is the end of the linked list on the left side, right? So what we do is, oh yeah, that's how you find the head and tail of the left of the left link of the left. Oh, let me do it again. That's how you find the head and tail of the flattened linked list of the left subtree, and then we just need to do a little bit of manipulation to put the left subtree, to put the node in the right place, which is the rightmost node, the dot right equals to now dot right, which is this one. And then now dot right equals now dot left, which is getting the head. And after we do that, so we already handled the root. The root has been handled. We are placing it in the correct order. And then we go to now dot right, right? And then we move on to the next one, which is actually the left child. Then we take that as the root, and then we do the whole thing again, right? So that will fix in the inside, and then once that is done, so we just keep going to the right, right? Keep going to the right, keep going to the right to finish every single one of them. Good solution, very good solution. I think I want to write this one again. Just good. Flatten left, flatten right. Okay, we flatten left, flatten right. Then what? Root dot left, root dot right equals left. That's okay. Tree node current equals root. And current dot right, now the root. So we walk all the way to the right, we walk all the way to the tail, and then right the current right equals right. This is not ON because every node, some node gets visited twice because of this thing, right? Because of this thing. Yeah, I think this is ON. Yeah, this is just you don't return it. You get it, the left and right, right, and then we want to find the end, that the tail of the left linked list. So they use this to find the tail of the left linked list, and then to link it back. Yeah. So this is a no. It does. It does visit twice. Yeah, it does visit twice. Okay, I think the best solution is definitely the reverse order, right? The right left node. That's definitely a good solution. But this non-recursive solution is also good. But is that ON though? Well, Pachman says it is ON. But you have to go all the way down. Yeah, is this ON? You sure it's ON? It is ON. It's the number of steps taken but not free. Yeah, so we go to the 4, then we append 5 here. there must be some savings. And then we go this one pass here, right? And then the 3, we go this one, go in here, and then go here. While now, I want to understand this ON. So we get everything. We get the left, right, most tree. We have to go through everything, right? Everything in here. Oh, but we go through everything in here. If you are already on the right, then you don't have to get moved. The only thing that needs to move is the left one. So once you go all the way down to the end, right, and then you make your move. You make your move. After you made your move, then you go to basically go to the put the left onto the right as well, and then you go to that node, right? Go to the left, and you always go to the left node. And that is problematic right now. And then you go through all the right nodes, but you don't do anything on the right nodes. You always go back to the left node. That is problematic. So every time you go through the right child only once, then you swap to the left subtree, and then go through the right child of the left subtree again, and the right child only get visited once. Yes, this is ON. This is ON. It's different from the other one. The other one is doing it twice. Let's try this one. Let's write this. Morrison Traversal. Okay, let's write this one. Yeah, I think this, like, you can imagine an interviewer will say, okay, how about we do this iteratively? Don't do it recursively. It's possible. This is the same idea. It's the exact same idea. Morrison Traversal from, oh shoot. Morrison Traversal from this, and I want to write it myself, so don't want to look at it. Same concept. It is the same concept as solution 1, but done in an iterative fashion with a lot more ingenuity. All right, so we have a root. So what we do is we need to find the left tree. I'm going to record it, right? So I'm going to say so I have the root, and I'm going to say the left is going to be root.left, right? And then when I go to the left, find everything inside what's the end condition? Now the end condition has to be there's no more left, right? There's no more left. That's why it says I call it now, right? And I would say while now, this is the left node. So we need to find the no. Now it has to be the root. Now has to be the root. No, now has to be the root. Now has to be the root. And then while the root. While now, right? And then we need to go for the left equals now dot left. And so left is now dot left. So now we need to find the rightmost of this, right? The rightmost of the left. So we say, what do we say? We say right equals left dot right, right? Well, if it exists, so if left exists, then right equals left dot right. And then while right equals right dot right. So we find the most right on the left tree. And after we find that, while right equals right dot right. No, it's actually while right dot right, because we don't want right to be none. So while right dot right. While right has a right subtree. All right, I'm going to change the name. This is going to be, so now the left is going to be the left head, right? This is head left. And we say if head left, I need to find the head right. So this is going to be head right. So this is going to be head left dot right. Now while head right dot right, then head right equals head right dot right. Keep going to the, so this is find the rightmost node on the left subtree, right? Say the rightmost node on the left subtree. After we find it, the head, not head right, what I'm saying, that's the left head, that's not head right, it's tail right. Tail left. Jesus, that's tail. Oh, we can just call it head and tail. Head and tail. Yeah, let's call it head and tail. So this is head, and this is going to be tail. So this is going to be tail. So these are tail. On the left subtree is the tail, right? So once we find the tail, then we know tail dot right equals tail dot right equals now dot right. Because now dot right, tail dot right, yeah, this is do this, and then head and then now dot right equals head. Yes. So now we handle these. We handle the left subtree already, right? Now we can jump out. So we handle it. Now we can move on to the next one. We can say, so now we handle the now. Now is handled. So we need to handle the next node. So now equals now dot right. So we can handle the next one. And then this one, handle it when it jump. So we all the way down when jump. So every time we go to the rightmost node of the left subtree. Now after we do that, we're going to jump to the left subtree again. And then once this is all done, we're going to go to the right tree at the end. Because every time we do this, and then we go again, that will jump to the yes. So now equals now dot right, going back, head equals this. If head, we do this. If not, we just keep going to the right. So we just shift everything to the right side, right? If there is anything on the left, we handle this by merging it to the right, and then we keep going. And at the end, oh, there's nothing at the end, and that's it. The rightmost node on the left subtree is the tail of the flattened left subtree. That is the key. This is the key sentence here. Now we're gonna make sure we document it well. Head is this is the head of the flattened left subtree, right? This is the head. So we have the head and we have the tail. Okay, let's try this one. Hopefully it passed because I am really hungry. I need to eat. We have an issue. Tail. Wait, how can we do this? Tail equals head. If head, while this head is in this, right? Head not right, then we cannot do. So we say tail equals head. And then if it's a single node, then tail itself. Then tail all right is not all right. Yes, I think this is, yeah. So this will give us output. Oh, shoot, I forgot to do the, where do we do that? So now the right equals head, and here, now the left equals none. Yep, let's submit. I have confidence. Yeah, very good. Very good. This is very good solution. Very good. One of the best. Morrison. I think this is not the first time. Also know Morrison Traversal. I used many different occasions. I forgot when, but I've used it before. Yeah, so this one, yeah, this is ON. ON because each right child is only because each right child is only visited once, is in the right place. Each right child is in the right place and does not need to be revisited. Actually, I think each one is visited twice. Each right child is in the right place and does not need to be revisited for modification. Each left child is visited. No, I think each one is visited twice, right? Because each node is visited twice. The right child is visited for the first time during the search for the rightmost node on the left subtree. It is visited again when we call now equals now dot right to walk down the already flattened portion of the tree. The left child is visited for the first time in head equals now dot left. It is visited again after head is place is moved into the right place, and now equals now dot right, and now equals now dot right leads the current now to the head position. Yeah, and then this is 28 milliseconds because we don't have the overhead of no, not this one. We don't have the overhead of recursion. So I think he is now correct. At most once. Oh yeah, he is right. He is right. Yeah. Okay, that's it. That's it for today. It's a very good question. Very, very good question. I am going to save this one. Add to list. I think it's a good interview question. There's so many different levels, right? You have the stupid. You have the not O1 space solution. You have a little bit stupid recursion. You have very, very good recursion, or the post order recursion, and you have the Morris and Traversal, like different methods. All right, good, very good. Okay, that's it for today. I will see you guys as usual tomorrow. Adios.